tenured professor of the Department of ECE at the University of Toronto. And from 2097 to 2008, he was his FPGA implementation tutor at Xilinx in San Jose and Toronto. And Professor Anderson has received 6 awards for excellent undergrad teaching, 3 best paper awards, over 25 US patents, and has also over 60 patent reference journals and a symposium. His research interests include all aspects of computer-aided design, architecture, and structure of FPGAs.
Okay. Great, thank you very much. Great to be here. Good morning, everyone. And thank you very much for organizing this workshop. It's a great idea, I think. So I'm here to talk about LegUp, which is a high-level synthesis tool that we're working on at University of Toronto. That's the LegUp research team. Right now we have 6 grad students that are working on LegUp. I think 3 are here at this conference, as well as some undergrads. The project is led by Steve Brown and myself, and we also are working closely with Altera on the project. Let me just start off very simply. You can think of there being 2 ways to do computations. You could write software, run that software on a standard computer. Perhaps inside there's an Intel processor, and maybe you wrote those computations in a standard language like Java or C. On the other hand, you could also do computations with custom circuits, and we know our phones contain many of such circuits. And of course, when you do computations with circuits, you're building a circuit that just does the kind of computation that you care about. Writing software, easy. It's not easy, it's comparatively easy. It's comparatively easy versus designing hardware. But of course, we know when we write software, we're running it on a processor, and that processor runs Google Chrome, it runs Excel, it runs PowerPoint, it runs a myriad of applications. The processors are always fetching instructions, decoding instructions. What do I do next? There's overhead, of course, with processors. There's going to be a power and speed overhead associated with that flexibility, that genericness of the processors. But with custom hardware, you're building a circuit that does just that one thing. So of course that's going to be more energy efficient and it's going to be faster than a very generic processor. But on the other hand, you need specialized knowledge to be able to do that, to design custom circuits. Hardware's potential. On this slide, what is the advantage you could get from doing computations in hardware versus software? I just chose a couple data points from recent literature on this front. So lithography simulation, 15x speed up in using FPGA hardware versus software. Solving math problems, linear systems, 2.2x speed up, 5x more energy efficient in using hardware versus software. A Monte Carlo simulation for a biomedical application, 80x faster, 45x more energy efficient. Options pricing, 4.5x faster, 25x more energy efficient. So you see the slide, it probably comes to your mind, well hell, why bother with software at all? Hardware is just fantastic, right? Just stick with hardware. Problem you can't do that is that hardware design skills are actually comparatively rare. Okay? Requires hardware description language, like Dirk mentioned in the opening. VHDL Verilog force you to work at a very low level of abstraction, level of individual bits. And actually, Dirk had the slide where he looked at the number of Google queries for software versus hardware. We actually looked at the U.S. Bureau of Labor Statistics. They gathered they look at the number of people in certain professions. Turns out there's 10x more software engineers than there are hardware engineers. Okay? So we really need a CAD flow that simplifies hardware design for software engineers. And so a solution to that is, of course, high-level synthesis. You're going to design circuits from software languages, from a software program. High-level synthesis, you're going to automatically synthesize a circuit, does the same computations as the program, give you some of the benefits of software programmability, with some of the hardware performance and power benefits. That's the idea. Now LegUp, it's a high-level synthesis tool that we started the project about 2009, about 5 years ago. Our input language is C, so we take C as input, and we produce a circuit in Verilog. That Verilog can then be read into back-end tools, say Xera tools. And the LegUp project, it's been pretty successful. We went public with it with our first release in 2011. And since that time, we've had about over 1,000 downloads of LegUp. And that's our website right there. If you go to our website, you'll see the picture. That's what it looks like. You can watch a video of Andrew talking about our LegUp tool. You could download our publications, tutorials. You could download the source code of LegUp. So it's open source for research and academic community. that's the website. If you look over the past year, just the visits to our website, we've actually had visitors from all over the world. So we actually got quite a bit of interest from really people all over the world that downloaded LegUp and tried out our tools. If you take a look at the most popular, where are most of our fans? Well, Canada and US is natural, but look at that, Germany. So it's long awaited that we have to come to Germany because our third most fans are here in Germany. Now, I was out jogging in my neighborhood in Toronto and jogging north of my neighborhood. I went into an affluent area, and then I was jogging along there, and on someone's fresh grass there, I see this, what's this, certified dog training on LegUp. So if you Google LegUp, get the high-level synthesis tool, not the dog training. And we're not affiliated with the LegUp dog training. So FPGAs and high-level synthesis. FPGAs, they're mainly accessible to hardware engineers. The FPGA vendors, Xilinx and Altera, they would love to blow open their user base and make it accessible to software engineers who could use them as computing platforms. There's 10x more software engineers than hardware engineers. Now you read some papers that say that high-level synthesis, the hardware generated, is good as a human-crafted expert. High-level synthesis tool does as good as a human-crafted expert. I'm not as optimistic on that. I think high-level synthesis can do very well in certain applications, say streaming applications, heavily pipelined applications. I'm doubtful on whether, for example, if you think of an FFT and think of how that's implemented in hardware, a spatial repeated butterfly layout, it's very tough for high-level synthesis to ever be able to synthesize something like that. However, for certain applications, I think high-level synthesis could do well. So, but I think there is a gap between high-level synthesis hardware and human-crafted hardware. Now, if you're going to custom silicon, you have to pay for every transistor, you have to pay for testing every transistor. Okay, so if there's an area gap, if you're using more transistors, that's more costly. On the other hand, if FPGAs is your target, as long as your design fits in the device, it's probably okay, as long as you don't have to say bump up to the next family member. Not only that, power and speed is one of the reasons you want to go to custom silicon to begin with. If you need the highest speed or lowest power, you can go to custom silicon. So for these reasons, I think FPGAs are likely the IC media through which high-level synthesis goes mainstream. Just say a couple slides on how does high-level synthesis work, just to set the context probably for the rest of the day. The typical flow is like this. You start off, we take a C program, bring it into a compiler. We're using the LLVM compiler, I'll talk about it in a second. And then you go through the typical high-level synthesis steps there, which are shown in blue. Allocation relates to defining the structure of the hardware. How many floating point adders am I going to use? How many dividers? So it's really setting the constraints on the hardware. And of course that's based on user constraints and a characterization of the hardware. Then you have scheduling, binding, and finally generating the synthesizable Verilog. We'll just say a few words about each of these things. Now we implemented LegUp in something called the LLVM compiler, which is an open source compiler. You've all heard of GCC, you may or may not have heard of LLVM. LLVM stands for low-level virtual machine. It's an open source compiler framework. It's very trendy now in compiler research. It's used in both companies and academia. If you actually build applications for Apple iPhone or iPad, their compiler is based on LLVM. It's also used by NVIDIA. Gives competitive quality with GCC. So LegUp is actually back-end passes of the LLVM compiler. Now, LLVM takes your C code and it's going to compile it into a control flow graph. Okay, it's going to perform many, many optimizations on that C code. In fact, there's over 50 different optimizations in LLVM. And it's going to compile it into a control flow graph. It looks kind of like this. If you see the C code here, you have some code, you have a loop, and then some code after the loop. It's going to be a control flow graph that looks like this. Some code here in a basic block. We'll see what that is in a second. You have a loop looping around right there, and then some code after the basic block. So you really have this graph of what's called basic blocks. And a basic block is just a chunk of code with a single entry point and a single exit point. That's what compiler people call a basic block. So here's an example of a basic block which maybe does some loads, additions, and a store. So LLVM really takes your C code, optimizes it, and produces this control data flow graph. It's a control flow graph with these basic blocks. And in LLVM, it brings in the C and it translates it into this new form where the basic blocks contain these very primitive computational operators that look like assembly code. They look like the assembly code you're familiar with probably from way back. contains shifts, adds, divide, XOR, these very, very simple instructions, as well as control flow operations, branch and call and so on. And that intermediate form in the compiler people call it intermediate representation. So LegUp does high-level synthesis directly on that intermediate representation. That's basically our input. We're operating on these low, simple, primitive machine instructions, shift, add, divide, and so on. Let me talk a little bit about scheduling. Of course, when we write C code, there's no notion of a clock at all. We just write the computations that we want, right? On the other hand, we know circuits have clocks. So scheduling is the task of basically taking these computations from the C code and putting them into clock cycles, and that really produces a finite state machine that defines which operations are going to trigger in different clock cycles. So if you look at that C language snippet right there, where we have some additions, a subtraction, and a multiplication, scheduling has to consider which operations could happen at the same time, which depend on each other, and it also has to consider timing constraints generally. Say an add takes 5 nanoseconds, a subtract takes 5 nanoseconds, and a multiplication takes 10. Let's say the user targets 100 megahertz, 10 nanosecond clock period. Scheduling has to consider that. So one solution to that scheduling might come up with is like this. You might put 2 adds in the same clock cycle, have parallel operations. You also might chain together some operations in a second clock cycle like that. That's called chaining. Now in LegUp, we use a scheduling algorithm that's from the literature called SDC scheduling. And basically in this form of scheduling, the scheduling problem, that assigning the computations to clock cycles, is formulated as a big math problem, as a linear program. Okay? And this approach for scheduling was actually published in DAC 2006. And so we formulate scheduling using this SDC scheduling, and you can go and check out that reference for exactly how that works. So we have an existing scheduling algorithm in LegUp. Now, an important thing you want to do in high-level synthesis in scheduling is something called loop pipelining. In loop pipelining, this is really a key concept in high-level synthesis. In loop pipelining, we're going to overlap loop iterations to produce a much, much faster circuit. And this is actually crucial for high-level synthesis to get good speed. So here's an example of a loop which does 3 additions. One way to schedule that loop is you could do 1 addition in each clock cycle. And let's say that would, if we had n iterations of this loop, it would actually take 3 n clock cycles to get all the work done. Make sense? And we would only be using 1 adder in each of the clock cycles. So our utilization there of adders is kind of 1/3 in terms of their busyness, right? Now in loop pipelining, we try to realize we could overlap the loop iterations in a way that looks like this. Say in a first cycle, we do the first addition of the 0th loop iteration. In a second cycle, we do the second addition of the 0th loop iteration, the first addition of the first addition of the first loop iteration. And finally, in the third cycle, we actually have 3 loop iterations that are in flight at once. And if you look at that, we're still using 3 adders in the steady state of the loop pipeline, okay? But they're fully utilized. They're all busy in every cycle. Now you can actually see the huge performance benefit of loop pipelining. We just went from 3 n cycles to n plus 2 cycles, okay, to get the work done. So that's the key concept in high-level synthesis, loop pipelining. Now if you look here, we were able to start a loop iteration on every single cycle. We started a new loop iteration. So we say here that the initiation interval, how often we could start a new loop iteration, is 1. Start a new loop iteration every cycle. But you can imagine loops could have iterations that depend on previous iterations. That could limit our ability to start an iteration. Maybe we can't start it every cycle. Likewise, there could be constraints on the resources that could limit our ability to start a loop iteration every cycle. So loop pipelining really wants to start a loop iteration as fast as possible, ideally every single cycle starting a loop iteration. Now, last thing I'm going to say about high-level synthesis before I dive back into what we're doing in LegUp is just want to talk a little bit about binding. That's another key step in high-level synthesis. With binding, imagine a C program where I had, say, 10 division operations in my C program. But let's say in my hardware I only have 3 divide units. Okay? I have to take each of my 10 division operations and assign it to one of my 3 divide units. I have to bind it to one of my 3 divide units. And that is called binding. That's a step in high-level synthesis. And in LegUp, we use a bipartite matching graph-based approach to binding, where, let's say these are my division operations here in yellow, these are my different functional units. I'm going to match every one of my operations with every one of my functional units. Does that make sense? And there's typically some costing associated with doing that. You could imagine that if I have 10 division operations and 3 dividers, I don't want to take all 10 and put it to one divider, the other 2 are just sitting there not doing anything, right? So there's some costing there to balance the assignment of operations to the units. So to give you an example of that, here's a little example that has, it's a made-up example with 7 multiplication operations. You can see in a first state there we use 3 multipliers, and so we might have 3 multiply units in the hardware. And let's say we bind them like this. We take this guy, we assign it here. We take this guy, we assign it here. We take this guy, we assign it here. Then we move on to the second state, and we bind this guy to here. Now we have 2 multiplications bound to this unit, 2 bound to this unit, 1 bound to this unit, and so on, like that. So at the end of the day, we have something like this. We have basically 3 multiplications sharing this guy, 2 sharing this guy, and 2 sharing this guy. And if you look at that, we need multiplexers in front of them to steer the right data in at the right cycle, to make sure the right data is going to each one at the right cycle. Those multiplexers are going to add to delay, so you do want to balance out the number of multiplications that is assigned to each multiplier unit. So that's just a quick primer on high-level synthesis, the key steps of high-level synthesis. Let's dive back into LegUp. Top-level vision for our flow goes like this. User would start with C program code. They compile it to a standard processor. Right now for us, that's a MIPS processor, software MIPS processor, or an ARM processor. Nothing here is unusual, standard stuff. The first change is that the processor, as it executes the program, it's gathering information about the execution of that program. The number of cycles spent in certain functions, maybe an estimate of the energy spent in certain functions, something about the memory access of certain functions. And what's the point of that? What we're going to do is we're going to use that profiling data to select chunks of the program that we're going to do high-level synthesis on and implement them in hardware as accelerators that talk to the processor. So we take those chunks, and by the way, right now for us, those chunks are at the function level of granularity. So we would synthesize whole C functions to granularity. So that's the granularity that we can convert these into hardware. That goes into high-level synthesis. And then those chunks of hardware corresponding to functions in the C are implemented on the FPGA, and the computer is still there. The original versions of those functions, they're ripped out, and they're replaced with wrappers that call the hardware accelerators, receive data back from the hardware accelerators. Okay. Now, I put that blue box around there to mean that the C compiler and the high-level synthesis, it's all done within this LLVM compiler framework, this open source compiler framework. Now, if you download LegUp, that's some of the features. You get the high-level synthesis, obviously. You get many benchmarks, including the 12 CH Stone benchmarks, which is a benchmark suite that's commonly used in high-level synthesis research. Automated verification tests. Okay, so for example, if you change the scheduling algorithm and you want to check, did I mess something up? You can run something that will tell you are all tests passing. Right now we support 4 different FPGAs: Altera Cyclone 2, Stratix 4, Cyclone 4, and Cyclone 5 SoC. You might notice there's no Xilinx FPGAs listed right there. They're all Altera FPGAs. Why? Well, Altera's funding us. We would like to support Xilinx. We just have to put some resources. Altera is funding us. But we would like to support Xilinx too, but we have to get some resources on supporting Xilinx. So right now we support 4 Altera FPGAs. And it's open source and freely downloadable. I don't know who here has heard of ABC logic synthesis. ABC is a logic synthesis tool from UC Berkeley that was made open source that a few years ago that actually spurred a whole bunch of new research in logic synthesis and what I consider to be actually a fairly mature field. So when we started the project, we thought, well, maybe for high-level synthesis, there's no good open source framework, and we thought maybe we could provide an open source framework. So that was another reason that we started the project, that we could become kind of like the ABC of high-level synthesis that allowed people to download a tool to try out new ideas in high-level synthesis. Now, what does the architecture look like when you run LegUp? If you're using the MIPS computer, it's a software MIPS processor. You have the MIPS there on the northwest side, 1 or more FPGA accelerators. Talk to the MIPS over a memory mapped bus interface. Don't worry if you've never heard of Avalon interface. Avalon interface, that's Altera's memory mapped bus interface. The computer and accelerators can share memory through an on-chip cache, as well as there's off-chip memory. And we actually support 2 Altera boards, a very inexpensive board called the DE2. It's like $200, very commonly used in digital logic labs, as well as we support a high-end Altera board, DE4, which has a Stratix board. That's a more research board, pricey board. Now, if you're targeting the ARM, the picture is just a little bit different. In the ARM, I'll talk more about it in a few slides. In the ARM, the cache is actually within the ARM processor itself. The hardware accelerators still talk to the ARM over the Avalon interface, and they can access the cache in the ARM. And I'll talk more about that in a second. And we support one Altera board, DE1 SoC. This is a rather puzzling to me marketing thing in Altera, which is that they had a DE2, a DE4, but now the newest board is back to DE1. You think DE1 was a 10 years ago board, but take my word for it, DE1 SoC is a brand new Altera board that incorporates the FPGA with the ARM processor. What do we support for high-level synthesis? Can we support the whole C language? We support functions, array structures, pointer, arithmetic, floating point. Some things we don't support for high-level synthesis. We don't support malloc and free. We don't have a heap and we don't have an operating system in the hardware. So right now we don't support malloc and free. Likewise, we don't support recursion. Okay, so if you have a recursive function, it has to run on the computer. We don't support recursion for the synthesizing part. But, partly because we don't have a stack in the hardware. It's a hardware circuit. Now, let's say you want to accelerate a function with LegUp. What would you do? Let's say you have a function here that computes a dot product, and you have a main function that calls that, and you want to take this dot product and make that into a hardware accelerator. So how would you do that? What you do is you write set accelerator function dot product in a tickle file. That tickle file is going to get picked up by LegUp. Okay? And what's going to happen is that function, LegUp is going to synthesize that into a hardware accelerator. Now the original version of that function is going to be ripped out and replaced with a wrapper. It looks like that, kind of gobbledygook. But these are memory mapped writes and reads over to the accelerator. Okay? And this new wrapper function, we call it a wrapper function, the original call to dot product will be replaced with a call to the wrapper function. Okay? And then this whole code right here is going to run in software on the computer. So all that will run on the bits or the ARM processor. Now, when you download LegUp, you get many benchmarks, including the 12 Sea of Stone benchmarks, which came from a university in Japan. A beauty of these benchmarks is that the input test vectors and output correctness checking is actually part of the benchmarks themselves. Okay, so the benchmarks have within them injecting vectors and making sure the output is correct. That's of course beautiful when you start a project like this, because when you're writing your own high-level synthesis tool, of course nothing works. Of course, you're getting the wrong logic functionality. At least with these circuits, you can tell, are you getting the correct answer? And they come from different domains: arithmetic, encryption, processor, and so on, media. Now, let me talk a bit about results, and then I'll go on to the kind of stuff that we're working on now. In our first release, which was 2011, we actually came up with several ways of evaluating it. We thought, first of all, we could take these benchmarks, we could run them in pure software on the mix, meaning to just forget about doing any high-level synthesis, pure software. Alternately, we could explore the software-hardware space. We could take some of each benchmark, we run it in software, some and run it in hardware. That's number 2. Number 3 was we run some in software, more in hardware. And number 4, we could take the entire benchmark, run it in pure hardware with LegUp. And number 5, we managed to get one other high-level synthesis tool that would allow us to compare with them, which is called Excite, which is from a company in California. And they allowed us to compare with them, so we were able to compare with one other commercial tool. High-level synthesis, there seems to be a tremendous amount of insecurity in the commercial high-level synthesis tools. Once I spent 1 hour on the phone with the university program for Catapult C. I said, can you give me Catapult C? And he said, well, who are you? And I said, who I am, and things like that. And he said, what do you do there? And then I said, well, I work on CAD tools, high-level synthesis tools. He said, we can't give you that. They want to give it to someone who works on communication algorithms to implement algorithms. They don't want to give it to someone who's going to try to be figuring out what it's doing inside. But give a lot of credit to Excite for allowing us to compare with them. So in our first release, the results look like this. On the west axis here, you see wall clock time, execution time, and that goes with the line right there. And here you see software, some hardware, some software, more hardware, pure hardware, Excite, pure hardware. What you can see is as you map more and more computations into hardware, you actually get about an 8x improvement. This is for the CH Stone circuits geometrically. On the right axis, you see their area, number of logic elements in cyclone 2, which a logic element in cyclone 2 is a 4-LUT flip-flop pair. These two middle bars, they're very high bumps because they contain the MIPS and accelerators. These rightmost bumps, there's no MIPS, just completely pure markers, so they call that. When we compared with Excite, in actually execution time, and by the way, we were running Excite in completely push-button way. We did not try to set tons of constraints to optimize the hardware, so that's the caveat of these results. When we ran Excite, we were actually a little better than Excite in terms of wall clock time. We were a bit worse than them in terms of area, but in terms of area delay product, we were roughly flat with Excite. So when we saw these results, we were encouraged that we weren't completely 10x off a commercial tool. We were kind of okay. We're not terrible. Now, our most recent public release is LegUp 3.0 from last year. And what do the results look like in 3.0? Here you see the CH zone circuits in 4 bars, wall clock time, number of cycles it takes to do the circuits, Fmax, as well as the number of logic elements. And what you can see, wall clock time, we're about 16% better, cycle latency, 30% better, Fmax, worse, okay? So sometimes it turns out in high-level synthesis, if you use a longer clock period, you can chain together multiple operations within one clock period, and that can reduce your number of cycles. As long as your number of cycles is reduced by more than your clock period got worse, you can end up with a winning wall clock time. So we effectively tuned for wall clock time. Area a whole lot better, about 28% better. Now, our current work is listed right here. We've been working on improving the loop pipelining, and please watch Andrew's paper on Wednesday. We've been working on debugging for high-level synthesis, which I think is a really important topic to consider. Please watch Nazanin's paper also on Wednesday. Adding support for an ARM processor, P-threads and OpenMP. We've been working on multi-cycle paths where we allow some combinational paths to have more than one cycle to complete. Looking at optimizing the memory architecture. Scheduler code motion where we collapse parts of the control flow graph. We've also been looking at, which Dirk talked a little bit about, why are there no FPGAs in data centers? So we want to eventually have a flow where LegUp accelerators could be used over PCIe with x86 processors, maybe in data centers. And how to incorporate your own IP cores into other LegUp generated circuits. I'm just going to talk briefly on these blue ones right here. And these I'll leave for another time just to move some time. Now, where are we now versus 3.0? If you actually, 3.0 was our last public release. What are we seeing right now in terms of quality of results in our current head branch? Wall clock time, we're a bit better even than 3.0, about 10% better. Cycle latency a little worse, Fmax much better, and area about 20% better. So we're planning, hopefully, to do another release of LegUp 4.0 this fall, which will contain these improvements. Now, on Wednesday, Andrew here is going to present a paper on improved loop pipelining, and I just have one slide to encourage you to come to that talk. What Andrew has done is he's come up with a new way of doing loop pipelining, which handles loops with two specific criteria. One is when you have loop carry dependencies, when you have an iteration that depends on previous iterations, like this kind of situation right here. And when you have resource constraints, meaning, for example, in this case, if you notice this loop right here, we have a dependency between loop iterations, and we have 2 loads and a store. We have 3 memory operations, but conceivably we might have a memory that can only is dual port, right? So there's a resource constraint. So with loops, with loop carry dependencies and resource constraints, with this work we can actually do much better performance than state of the art in loop pipeline. Find out how on Wednesday at 10:45. So please come to the session on Wednesday at 10:45. Now, debugging is actually, I think, a really important topic in high-level synthesis, because it can't be the case that you run high-level synthesis, okay, you get this automatically generated Verilog, it's 10,000 lines, you put it in the system, bang, it doesn't work. If it truly is FPGAs for software programmers, you can't say to the software person, open up ModelSim and look at the logic signals and clocks and clock skew and all that stuff. It can't be. We need debugging tools and visualization tools that software people have a hope of understanding. So Nazanin has built sort of a first step towards debugging, and her debugger looks like this, where you can actually step through the C code And as you're stepping through the C code, you'll see the corresponding LLVM machine code inside LLVM, as well as you'll see the corresponding Verilog. And you can look at variables, but the values of those variables are actually extracted from hardware running under the hood, either in ModelSim or actually in silicon. So find out more on Wednesday at 13:30 session on Wednesday. So that's just a taste of that. Now, I want to talk about, just in the last little bit here, I still have some time, good. I'm going to talk about two things in a little more detail that we've been working on recently. We've been adding support for this ARM processor, and we just presented that last week in a conference in Milan, embedded in ubiquitous computing. Now, these new Altera FPGAs, Cyclone 5 FPGA SoC, it has a hardcore ARM embedded in the FPGA itself. It's a 28 nanometer FPGA, and that ARM, it runs fast, okay? It runs at 800 megahertz. Now, each ARM core, it's a dual core ARM, has its own level 1 cache, I'll show that in red, and they share a level 2 cache, and the FPGA accelerators can access the ARM cache. A detailed architectural picture is shown right here. Here you see the two ARM cores. They have their own cache. These caches can be kept consistent by a Snoop control unit right there. FPGA accelerators will be hooked up off the FPGA bridge right here, and they can talk to the ARM cache through this, what's called accelerator coherency port. Okay, there's the L2 cache. The FPGA accelerators hooked up on the top can also access off-chip RAM through an SD-RAM controller. The person who actually did the work on this is Blair Ford. He's here, so if you have questions on it, you can look at our EUC paper or talk to him about it after. That's all I'm going to say about it. There's a lot of details in terms of the way that the processor views the memory space versus the FPGAs view the memory space. Now, it turns out when you have an 800 megahertz ARM processor, it's a lot harder to get speed up versus if you're using a soft-core MIPS, as you might imagine. A soft-core MIPS, say, runs at 80, 90 megahertz versus using an 800 megahertz ARM processor. So the C.H. Stone circuits don't contain many opportunities for loop pipelining. It's very hard to accelerate those over the ARM processor. So kind of as a showcase application that we can, it's actually very nice to get speed up, is computing the Mandelbrot set. Now, it turns out that you've probably all seen images of this Mandelbrot image right here. Computing the color of every pixel in that image, it's very, very compute intensive. Okay? Not only that, each pixel can be computed completely independently. So it's one of these kind of embarrassingly parallel applications. Okay? So this is an application that's very compute intensive. It's a compute-bound application, and so we have chosen this as kind of at least an initial showcase piece for accelerating the ARM processor. Plus, this can all be done in fixed point calculations. I'm going to show you here a video of three things. We're going to see the zooming in of the Mandelbrot image, first on the ARM processor, 800 megahertz ARM processor. Over here we'll see LegUp pure hardware, okay, where we took the C to generate the Mandelbrot, we synthesized it with LegUp, there's no processor anymore. And over here we're going to see LegUp pure hardware where we applied loop pipeline. Okay, let's take a look at the video of these three different cases. By the way, the LegUp accelerators are running at less than 200 megahertz. This is actually a beautiful example of how, if you can tailor the hardware circuit to the computations, you can actually get much, much better performance over a processor that even runs multiple X faster. On the top there is the 800 megahertz ARM. Lower left, vanilla high-level synthesis where we didn't set any constraints. Lower right, where we applied loop pipelining, okay, in the high-level synthesis. And this is just one high-level synthesis circuit that's doing that. Okay. You can actually see huge speed up over 800 megahertz ARM for a certain kind of application. Okay. Now, when we ran in the hybrid flow, where we have the ARM working with accelerators, we get these results. Here you see the ARM pure software, one LegUp accelerator, two LegUp accelerators, each working on different parts of the image. Okay. Remember, each pixel can be computed independently, so that's easy to do. 4 LegUp accelerators, 8 LegUp accelerators. You can see with 8 accelerators, you can actually get about a 5x, almost 6x speed up versus software. The interesting thing is, look at these red bar, which is the speed of the circuit in megahertz. With 1 LegUp accelerator, it's running at just over 120 megahertz roughly, versus 800 megahertz arm. So to me, that's just incredible. When you can tailor the circuit to the application, you can get that kind of peak speed, even though the circuit's running much, much slower. The last thing I'm going to talk about, just to close, is something that we're quite excited about, and we think this is sort of one thing that's unique in LegUp, as far as the capabilities of our high-level synthesis tool, relates to exploring spatial parallelism. Now, speed benefits of hardware arise from parallelism. Okay? We want to be able to use that as much as possible. However, extracting parallelism from a C program, that's pretty hard. Okay? So, auto-parallelizing compilers, there's been ideas on auto-parallelizing compilers for a super long time. To me, it still is not that yet mature. But we know software people know how to write parallel programs. So we had this idea that if software people write parallel programs, they might use pthreads and OpenMP. Why don't we synthesize parallel hardware from the software parallel program? So that's the idea. So if you kind of look at the spectrum of programming models from the parallel angle, on the one side you have sequential in C and C++. On the other side you have this massively parallel, thousands of threads, which I think Peter and Boris are going to talk about this afternoon. You know, languages like CUDA and OpenCL, and Altera has opted for using OpenCL in their high-level synthesis. In the middle is when you probably have fewer threads, maybe they're doing bigger, more heavyweight things, pthreads and OpenMP. So we decided to add a high-level synthesis support for pthreads and OpenMP, and those are actually C standards. So the idea is that parallelism in the software is going to be automatically synthesized into parallel hardware accelerators. We also provide support for 2 synchronization constructs in parallel software, mutexes and barriers. Now, if you use pthreads, you're going to have, say, a function which is adding up 2 vectors. Let's take a look at this little example. If you use pthreads, you have to explicitly create the threads. Okay, so we're going to launch, say, 4 threads in this example that are going to work on different parts of this vector addition. Now, when you create a thread, you're passing in a thread variable, the name of the function that you're running in the thread, as well as some data that you're passing to each thread. Likewise, you have to join back the threads at the end. You pass in the thread variables, and you get results back from each of these threads. Okay? Now, in this example right here, we'll fork 4 different threads at the add function. Okay? OpenMP, well, it looks like a thing of beauty compared to that pthreads example. We want to parallelize this loop right here, which is doing a dot product. We use special compiler pragmas right here. We say pragma OpenMP. We say it's a parallel for loop, 2 threads, and we want each thread to have its own private induction variable I. This would fork 2 threads, each operating on different parts of the loop. Now, in LegUp, what we do actually is for 4 threads right here, we're going to generate 4 hardware accelerators. Okay? By the way, right now, as far as LegUp goes, the number of threads that you fork is the number of hardware accelerators that we generate. Okay, so meaning you can't fork 1,000 threads and have 4 accelerators because we don't really have an operating system that is scheduling threads and doing context switches and things like that. Now, of course, just like before with the hybrid support that I talked about, we're going to have wrapper functions that replace the pthread functions. So pthread create and join are going to be replaced by wrapper functions that basically invoke the accelerators and wait for them to complete on the join. And all that chunk right there is going to run in software on the MIPS or the ARM processor. And all the generation and replacement are done automatically using the LLVM compiler passes. Likewise with OpenMP, we'll generate 2 hardware accelerators, we'll have wrapper functions, and that will all run in software on the MIPS or the ARM processor. Now we also do support a form of nested parallelism. You could imagine that you have threads which are doing different functions, add, subtract, and multiply. But imagine in those you each had a loop inside those threads, and you wanted to parallelize that loop, say with OpenMP. Well, you might have this situation right here where you sort of have threads forking threads. We call that nested parallelism. And up to 2 levels, we support that. That's it. We don't support threads forking threads forking threads forking threads. Up to 2 levels, we do support nested parallelism, where you end up with a circuit that looks like this. We have our level 1 accelerators, add, subtract, and multiply. And let's say inside we have these OpenMP accelerators, where we parallelize a loop with OpenMP. We call those level 2 accelerators. Okay, so let's pick it up from here. Great. So we support a form of nested parallelism. So just show you a few results on here, and the main takeaway of this is that through software changes alone, you can explore an incredibly wide range of parallel architectures. That's the main takeaway. So through software changes alone, we actually used our threads in OpenMP to look at 11 different architectures for circuits. Single-threaded, 4 level 1 threads, 4 level 1 threads with loop pipelining inside, as well as different numbers of level 1 and level 2 threads, where in some cases we actually had up to 120 accelerators, where kind of 30 were level 1 threads, and inside each of those had 4 OpenMP accelerators. And we used 7 benchmarks for this, and targeting the Altera Stratix 4. To show you a few results highlights. Here you see the architectures going from sequential up to that case where we had 120 accelerators. There's different lines is because not all architectures were relevant for all benchmarks. Okay, so this is all benchmarks. The red line is the division, Mandelbrot, and hash benchmark. The green line, division, Mandelbrot, and line of sight. But what you can see is generally more parallelism to the right. Now, up to a certain point, we're seeing speed-ups. On the vertical axis here is speed-up. Up to a certain point, we're seeing speed-up. Beyond that, though, we really are seeing a slowdown because there's just too much contention. There's too many things competing with each other, for example, the memory accesses. Now, for all circuits, we saw a 7x speed-up, 7 to 8x speed-up over the pure sequential case. Now, of course, as I said, not all lines could contain all circuits. Not all architectures were relevant for all circuits. For division, Mandelbrot, and hash, 4 level 1 accelerators with loop pipelining inside, 6x speed-up. With 4 level 1, 4 level 2, so 16 accelerators, 7.5x speed up. The biggest gain we saw was for these circuits right here, we saw about a 13x speed up with 4 level 1 accelerators and 4 level 2 accelerators. We also looked at the area delay product. And the main takeaway what I want you guys is not so much the numbers, is just through software changes alone, you could explore all these different parallel architectures. Imagine if you had to recode VHDL or Verilog to instantiate different numbers of level 1, level 2 accelerators, get them doing the right thing at the right time. It's a really complicated problem. So this is something that we're quite excited about that I think is sort of unique to LegUp. So just to summarize, it's an open source high-level synthesis project. It targets this hybrid system, the processor accelerator. If you download it, you get the LegUp tool itself and many benchmark programs and other infrastructure. Active development continues in the areas that I talked about. How would you get started with LegUp? If you download LegUp, I think the best way to get started is to click on tutorials on our webpage. And we actually have several tutorials that walk you through how to use the tool as well as how to modify the scheduler. For those would be interested in people who want, those would be interesting for people who actually want to try modifying their own high-level synthesis tool. We also have a new tutorial that we just used about a month ago at a course in Hong Kong. It takes you through that Mandelbrot example and using LegUp to generate 5 different versions of Mandelbrot with all kinds of different performance. Questions?
Thank you, Jason.
Thanks, Dave.
Questions?
Yes. Question. We talked about speed up. It's kind of interesting, right? I mean, that is system where you also get trouble with performance constraint at the same time with power constraints, power consumption. Can you say something about this like power consumption? Because in the last slide we showed Mandelbrot speed up 7 factor by using an 800 megahertz ARM, but how was the clock for the FPGA? How was the power energy consumption for this?
We didn't look at for the embedded ARM bit where we accelerated the Mandelbrot. We didn't look at power consumption. We did last year. I mentioned that we're also working on LegUp accelerators over PCIe, right? We did also accelerate Mandelbrot with the x86 processor over PCIe with LegUp accelerators, and we looked at power consumption actually measured from the wall socket in that case, and we were 5x more energy efficient. We need to look at the power consumption with the ARM processor. We haven't looked at that yet. Now, in the original results where we had the MIPS processor with LegUp accelerators talking to the MIPS, I didn't show the results here. We did evaluate power in that case, running CH-Stone on the MIPS versus accelerated CH-Stone with accelerators. And in the original LegUp paper, you can see the power consumption for that. We had a more than 10x power reduction. I believe it's 18x power reduction comparing to running in software on the MIPS.
Yeah, with software and this will be the key factor for success.
I completely agree. I think these processors, they're really fast. 800 megahertz is pretty fast, right? And the x86 are running in gigahertz. Right, so perhaps energy is going to be kind of the winning argument, right, for FPGA-based acceleration. Yeah, good question. Yes.
The case where you get the one where you convert the two time, you just find enough resources in FPGA.
Sure. That was even in the parallel examples. Why some architectures weren't relevant for all benchmarks is because sometimes you just blew out the size of the FPGA. Does that make sense?
So what do you do?
We haven't done anything on dynamic reconfiguration. We need to hook up with some of the third stuff probably to swap in and swap out accelerators. We haven't done anything like that, and also our support for that is not that strong. So meaning that, say I choose this function, this function, this function, and this function to run as accelerators, and let's say I can't fit it on the FPGA. You yourself would have to go back and get rid of some of those lines in the tickle file. You would have to basically manually move some back onto the processor. Meaning we don't have good support in terms of models of the Altera devices and estimates of how much area we're going to use and trying to predict, are we going to exceed that amount? We haven't spent a lot of time working on that. So if it doesn't fit, that's your problem. Move more into software right now. You had a question there?
Only one short question, then we can have to postpone the question to the conference. Short question.
I have a question about memory access.
Yeah.
What's going to access irregular, not through access?
Question is can LegUp access memory irregularly or indirect or not stream access? So the question, yes, that's absolutely fine. So any memory access to any location is fine. Okay, but I think where you're going is that imagine in a C function, if I declare an array and I take that function I put as an accelerator. If we can reason that that array is only accessed in that function, then we can keep the memory in that Verilog module. We don't need to make it accessible to all Verilog modules, so we do that. But for chunks of memory that we can't reason that they're only going to be accessed locally, we have to kind of put those outside, and all accesses to those go through a memory controller, which will, I think, in which the memory controller will resolve the addresses to steer the memory request to the right block around. So it doesn't have to be irregular memory access, completely fine.
Okay.
Come talk to me at the break for more questions. I know there was one question here, so that's chat.
So thanks, the speaker. For Oktoberfest.
Well, thanks, Dave.
Okay, now we have our fast forward for the poster presentation. We have only 20 minutes for 9 posters, so it's only 2 minutes per presentation. So please come here, and the next speaker will be in back here, and so we have a fast turnaround.